press the bell icon on the YouTube app and never miss another update.
Hello students, in the previous class, that is class number 12, we have discussed some basic terms: Emf of cell, internal resistance of cell, terminal potential difference, external resistance, electric circuit, etc. Right? Now, EMF of a cell is the work done or energy spent by the cell in driving unit positive charge once around a complete circuit. It is EMF is equal to work done by charge. It is its SI unit is volt. Now, internal resistance of a cell is the opposition offered by electrolyte and electrodes of the cell for the flow of electric current through the cell. Internal resistance of a cell is the sum of the oppositions offered by electrolyte and electrodes of the cell, right? Obviously, its SI unit is ohm. Terminal potential difference across a cell is potential difference across the terminals or electrodes of the cell when the cell is driving current in a closed circuit. Now, so far from Ohm's law, we know how to calculate current flowing through a conductor. That is, I is equal to V by R, where V is potential difference and R is resistance. So far we have considered either a conductor or a resistor or combination of resistors to which potential difference V is applied and we can calculate the current. But now what provides potential difference for a conductor or resistors? It is a cell or a battery called source of EMF, electromotive force, that provides a potential difference between the 2 points of a conductor. Therefore, for the flow of current, we need to connect a cell or a battery to a conductor or a resistor. That forms an electrical circuit. Simple electrical circuits, right? DC circuits particularly consists of resistors connected to a cell or a battery, right? In AC circuits, we are using resistors, capacitors, inductors along with an AC source, AC generator or AC right dynamo. Here we will find an expression for current through an electrical circuit. Now we have found expression for current through a conductor, right? Let us recall that one. I is equal to NEAVD. This is the expression for current flowing through a conductor in terms of microscopic things, right? Electric charge, area of cross section, number of free electron density, right? And drift velocity, right? But here we are going to derive an expression for, right, current flowing through an electrical circuit in terms of EMF of cell, internal resistance of cell, right, and external resistance, right. At the same time, we will also derive an expression for terminal potential difference across a cell, right. Now, that is the derivation. Expression for current in a circuit, right, as well as terminal potential difference across a cell. It is a 3 mark or 5 marks question in board examination, right? Now let us consider a cell of EMF E and internal resistance R, right? Now a cell is represented by, as shown in figure, the long line represents positive terminal, short line represents negative terminal. Now the cell is connected to an external resistance R, right? Here the solid lines what I have written here, through which we can connect cell and resistance, they are called connecting wires. Generally in any electrical circuit, the resistance offered by, right, connecting wires is negligibly small, right? We won't consider here, right? But here the resistances are two: internal resistance small r, external resistance capital R, and EMF of the cell, right? So when we connect cell to a resistor, and that provides a potential difference between the ends of the external resistance V. This is called the terminal potential difference, and there is a potential difference across the terminals of the cell, right? This potential difference is from positive terminal to negative terminal through external resistance, right? At the same time, there is an potential difference across internal resistance of the cell, because we know that what is potential difference? Potential difference between any 2 points is the amount of work done in driving 1 coulomb of charge from one point to the other point against the field, right? At the same time, from Ohm's law, we have V is equal to IR. So potential difference is the product of current and resistance. Whenever a current flows through a resistance, then potential difference across the resistance is equal to, right, current into resistance. Here V, capital V, represents terminal potential difference across external resistance, right? And the V dash represents terminal potential difference across, right, internal resistance. What is resistance? Resistance of a conductor or a cell, internal resistance, is the opposition offered by the cell or conductor for the flow of current through it. In order to maintain the current or drive the charge, work has to be done or energy has to be done, right? That energy is spent by this cell. By definition, what is EMF of a cell? EMF of a cell is the amount of work done in driving 1 coulomb of charge once around a complete circuit, right? So by definition, EMF of cell is equal to work done in driving plus 1C, 1 coulomb of charge, right, through complete circuit. That is once around a complete circuit, right? Or EMF of cell. See here. Now this work is done against the opposition offered by external resistance and against the opposition offered by internal resistance, right? So this is equal to work done against or plus work done against small r, that is the internal resistance, right? Therefore, internal resistance of cell E is equal to potential difference across external resistance R plus potential difference across internal resistance R. Remember that, right? V is equal to potential difference is equal to IR, right? Now that EMF of cell E is equal to, right, it is V plus V dash. Potential difference across external resistance plus potential difference across internal resistance, or E is equal to potential difference across internal resistance. Say if I is the current flowing through the circuit, then potential difference across external resistance capital V is equal to IR plus potential difference across internal resistance is equal to, right, the same current flowing through internal resistance plus I into R, or taking E is equal to I common, R plus or E is equal to or. So current in the circuit I is equal to E by R plus R. Let us take it as equation 1. So this is the expression for current through a circuit where E is EMF of cell, right, R is external resistance and small r is internal resistance. This R plus R is called, right, circuit resistance, that is the total opposition offered by the circuit for the flow of current through it, right? And this equation 1 is also called Ohm's law applied to a circuit. When we apply V is equal to IR or I is equal to V by R, it is the Ohm's law applied to a conductor where it gives current flowing through a conductor. But Ohm's law when applied to an electrical circuit, it takes a form I is equal to E by R plus R, and it gives the current flowing through a circuit. Once again I repeat, right, expression for current through a conductor is I is equal to NEAV suffix D. Expression for current through an electrical circuit is I is equal to E by R plus R. Now, right. So here this terminal potential difference, right, is equal to potential difference across, right, terminals of cell in, right, closed circuit, right, that is potential difference between these 2 points, right. This point is connected to positive terminal, this point is connected to negative terminal, right. Now the potential difference between these 2 points, see here, is equal to potential difference across external point. This is also equal to potential difference across external, potential difference across external resistance, right. So here the cell provides a potential difference for the flow of current through a conductor or resistance R. Here two conditions are satisfied to obtain electric current. One, there must be a potential difference provided by the cell, and there must be a conducting path provided by conductor or resistor, right? Therefore, this terminal potential difference V is equal to, right, I into R, right, where I is current and R is resistance, right? So, this V is equal to, but I is E by R plus R. Therefore, this is equal to E into R by R plus R. So, the terminal potential difference depends upon current as well as circuit resistance. But EMF of cell is independent of this circuit resistance. EMF is constant for a given cell or a battery. It depends only on nature of electrode and the nature of electrolyte. Is that clear? This expression, say equation 2, gives the expression for terminal potential difference across a cell, right? So, the question in board examination may asked in two ways. One, derive an expression for, right, current in an electrical circuit. That will be for 3 marks only. You have to derive up to this equation 1, I is equal to E by R plus R, right? Or the question may be asked like that, right? Derive expression for terminal potential difference across a cell in an electrical circuit, right? In that case, you have to derive equation 1, right, and also equation 2. V is equal to ER by R plus R. Now, whenever we are having an electrical circuit, right, now current flowing through the electrical circuit is obtained by I is equal to E by R plus R. Right. Now, note number 1. So, current in an electric circuit I is equal to E by R plus R. That is, in general, current in a circuit is equal to EMF of cell or battery instead of cell if you use a battery. Now, this is R, external resistance plus internal resistance, right? Remember that electric current through a circuit is equal to, right, EMF of cell divided by external resistance plus internal resistance, or it is the sum of external resistance and internal resistance, and it is called circuit resistance. Suppose if, right, a number of resistors are connected to a cell in series or parallel or series parallel. whatever may be the combination. Then the effective resistance of the combination of resistors is equal to the external resistance. In that case, I is equal to E by Re plus R, where Re is right effective resistance of combination, where Re is effective resistance of combination, and Re plus R or R plus R in this case, right, is called circuit resistance. Is called circuit resistance. So remember these things, right? Now using this equation and Ohm's law, that is V is equal to IR, we can find current, potential difference, right? Suppose if there are combinations, parallel combination, what are the different currents flowing through parallel combination, right? And if it is series combination, what are the potential differences across the series combination, right? Is that clear? Now, note number 2. In a closed circuit, right, generally a circuit is made by connecting resistance to a cell along with a switch or key, right? So when key is open, no current flows through the circuit and it is called open circuit. When the key is closed, when I put a dot here, the key is closed. When the key is closed, the current starts flowing through the conductor and it is a closed circuit. We say that the cell is discharging current, right? Now in closed circuit we have EMF E is equal to V plus V dash, or terminal potential difference V is equal to E minus V dash. But V dash is equal to IR. Therefore, terminal potential difference of a cell is equal to E minus IR. So, terminal potential difference of a cell, right, is given in terms of one equation which we have derived, V is equal to ER by R plus R. Another equation which for terminal potential difference in closed circuit, V is equal to E minus I into R, and this equation is used to find effective EMF and effective internal resistance of right combination of different cell. That is the next topic, right? Now this is the equation. Now see here, right? So generally that external resistance is greater than internal resistance. That internal resistance have a finite value. Therefore, that IR is less than V. IR is less than V because V is equal to I into capital R. When IR is less than V and has a finite value, right? So this V is E minus IR. That means terminal potential difference of cell is less than EMF of cell in closed circuit, right? Or right, terminal potential difference of cell V is less than EMF of cell, or E is greater than terminal potential difference when the cell is discharging current. When the cell is discharging current, right? Now the relationship between this EMF and in terminal potential difference of cell is important. Here we come across 4 different cases. Closed circuit, that means cell is discharging. Open circuit, that means cell is not charging or discharging. Third one, right, when cell is charging. Suppose we say we have a battery in our smartphones, right? So when we are using that mobile phone, when battery is down, what we will do? We will charge the battery, right, by inserting the plug of the charger. What happens now? Now the battery is charging. When you are using mobile phone, making a call or using social media, etc., that is the case where battery is discharging current and it is a closed circuit when you put off the switch, right? Right, when you put off the switch and not charging, right, the mobile phone is not functioning. No current is flowing through it. You are making it as an open circuit. And when it is charging, right, you put that one, right, charger into that one, right, and another one is short circuit. Now here, another important thing we have to discuss here is, right, when in closed circuit, right, see here, in closed circuit, current flows from positive terminal to negative terminal of cell through external resistance outside the cell. This is the direction of conventional current. So you see that the current flows from positive terminal to negative terminal through external resistance. This is the direction of current flowing outside the cell. But inside the cell, the current is flowing from negative terminal to positive terminal of the cell. Right. Now, inside the cell, current is flowing from negative to positive terminal of the cell, right? And therefore the potential drop, we say there is potential drop, we have lost that potential, right? Now potential drop, right, that is I into R opposes the EMF. It opposes the EMF. Therefore, V is E minus IR and V is less than E. Right? Suppose, as an example, when we say that EMF of cell is 1.5 volt, we are using it in a torch for 3 volt, we can take 3.0 volt, that is we are using in our remote controller of a TV, right, or even 2 cell small pen torch, right. That EMF is 3 volt, but the potential difference across is say 2.8 volt. That 3 volt of EMF will not completely appear as potential difference across the bulb, right, of the pen torch or in any circuit. It is because some part of potential is lost, and that appears as V dash is equal to IR is equal to 0.2 volt. Therefore, instead of getting 3 volt across the external resistance, that is bulb, we are getting 2.8 volt. How much potential difference is lost? Say 0.2 volt. Therefore, we call it as potential drop, right? That potential drop in closed circuit opposes the applied EMF, because here the current is flowing from negative terminal to positive terminal, right. Therefore, this potential difference across the internal resistance, it opposes the EMF of cell. Is that clear? The direction is very important in a closed circuit. Now, note number 3. So, now in open circuit, the cell is disconnected from that cell is disconnected from external resistance. So generally, when we wanted to have fan to be switched off, fan to be rotate, current has to be flow through it, and we will put the switch on. That is a closed circuit. Whenever we don't want the fan working, we simply switch it off. When it is switched off, no current flowing through the fan, and fan does not rotate. Now we say that it is in open circuit condition. Through the switch, we can make the circuit as closed circuit for the flow of current, and open circuit in which no current flows through it. So here, current flowing through this is equal to 0, this EMF. Now there is a potential difference again is across the terminal, terminals of the cell. There is a potential difference. This potential difference, is equal to EMF of cell. This potential difference is equal to EMF of cell, because this is at negative potential and this is at positive potential. Why there is no flow of current, it is because, there is no conducting path. The second condition is not satisfied. Potential difference is there, but there is no conducting path between these 2 points. That means there is an insulator. Therefore, resistance of, the open circuit is taken to be infinity, the circuit resistance. Instead, we can take here circuit resistance is equal to what? Infinity, and no current flows through it, So in this case, terminal potential difference, you got it? A circuit is said to be an open circuit when no current flows through the circuit and circuit resistance is infinite. In this case, terminal potential difference V is equal to. Now, terminal potential difference V is equal to, we have E minus IR, that is equal to E minus I, 0 into I, 0 into small r, right? So 0 into small r is 0, that is equal to E. So we can come to the conclusion that in open circuit, terminal potential difference, right, is equal to, right, now terminal potential difference is equal to EMF of cell. When I have given previous example, when 3-volt battery is connected to bulb of a pentouch, the terminal potential difference is 2.8 across the resistor and current flows through it. Remaining 0.2 appears across, right, internal resistance of the battery. But when the torch is switched off, now the potential difference across the cell or bulb is entirely 3 volt. It is the maximum value. It cannot exceed 3 volt, right? But, right, no current flows through the circuit because there is no conducting path, right? Now the terminal potential difference across the cell, that is V is equal to E. Now in this case, right, V is equal to E, remember. Therefore, we can give another definition to EMF of cell. EMF of cell, right, is also equal to maximum potential difference across the terminals of the cell when the cell is not discharging current, that is in open circuit, right? So EMF of a cell is equal to maximum potential difference across terminals or electrodes of the cell when the cell is not discharging current, that is in open circuit, right? So EMF of cell can be defined in two ways, right? So remember that EMF of a cell is equal to the maximum potential difference across the terminals of the cell when the cell is in open circuit and not discharging current. Now, the third case, note, when cell is charging. When the cell is charging. See here. Now, this is a cell of EMF E and internal resistance R. Now again a cell can be charged by using a battery, right? Now to charge this cell, it has to be connected to a battery, Now this is charging battery. It is a cell, right? Now see here, while cell is discharging, positive terminal of cell is connected to positive terminal of battery. Negative terminal of cell is connected to negative terminal of the battery. Generally, to charge a cell, the EMF of the battery must be greater than EMF of cell. Therefore, this point is at higher potential, this point is at lower potential. A current flows right through the circuit and the cell is discharged. In this case, there is a potential difference V, right, appears across the terminal of the cell. That terminal potential difference, right? Now here, when right cell is charging, right, so current flows right inside the cell from positive terminal to negative terminal of cell, right? And outside it is negative terminal of the cell to positive terminal. Don't get confused. Once again, listen. In closed circuit, cell is discharging current. Conventional current flows from positive terminal to negative terminal outside the cell. Inside the cell, that is from negative terminal to positive terminal. Clear? Now, in this case, when the cell is charging, the reverse takes place. Inside the cell, the current is flowing from negative terminal to right positive terminal, right? Sorry, positive terminal to negative terminal. Outside it is from negative terminal to positive terminal. Outside the cell, I flows from negative to positive terminal. Therefore, right, this potential drop across internal resistance, that is IR, it favors the EMF of cell. Now in this case, terminal potential difference V is equal to E minus of minus IR, right? Because this IR is in opposite direction, and in closed circuit IR opposes the EMF. In while cell is discharging, right, cell is charging, right, this potential drop across internal resistance, it favors the EMF. Therefore, it is V is equal to E minus of minus IR, that is equal to E plus IR. Now, since IR has a finite value, this terminal potential difference is right greater than EMF of cell, right? So, when cell is charging, terminal potential difference of cell is equal to EMF of cell, that is V is greater than E. the terminal potential difference across the cell is greater than E. In general, when cell is driving current, discharging, closed circuit, EMF terminal potential difference is less than EMF of cell. In open circuit, cell is neither charging nor discharging. Current is 0 and terminal potential difference is equal to EMF of cell. When cell is charging by a battery, now the terminal potential difference is greater than EMF of cell. Now, short circuit. You might have heard of the word. This is short circuit. ಎಲ್ಲಾದರೂ ಫ್ಯಾಕ್ಟ್ರಿಗಳಲ್ಲಿ ರೈಟ್ ಕಂಪನಿಗಳಲ್ಲಿ ಬೆಂಕಿ ಹತ್ಕೊಂಡಿದ್ದಾಗ ಫೈರ್ ಕ್ಯಾಚ್ ಮಾಡಿಕೊಂಡು ಎಲ್ಲ ಸುಟ್ಟು ಹೋದಾಗ ಅದಕ್ಕೆ ಕಾರಣಗಳು ಹುಡುಕ್ತಾ ಇರ್ತಾರೆ. ಬೆಂಕಿ ಎಲ್ಲಿಂದ ಬಂತು ಅದಕ್ಕೊಂದು ಕಾರಣ ಕೊಟ್ಟಿರ್ತಾರೆ. ಇನ್ನು ಶಾರ್ಟ್ ಸರ್ಕ್ಯೂಟ್ ಆಯಿತು, ಬೆಂಕಿ ಹತ್ಕೊಳ್ತು ಅಂತ. ಶಾರ್ಟ್ ಸರ್ಕ್ಯೂಟ್ ಅಂದರೆ ಏನು? ರೈಟ್. ಸೊ ವೆನ್ a cell is directly connected to the terminal, that is R is equal to 0. Remember that connecting wires have no resistance, right? Their resistance is very, very small. When external resistance is 0, a maximum current flows through the conductor, right? That I is equal to E by R plus R, that I maximum is equal to E by 0 plus R, it is equal to 0. So, a cell gives a maximum value of current when it is short circuited. Single cell I am talking, right? A cell or a battery gives maximum current when it is short circuited. When short circuited, right, external resistance is 0, right? Since internal resistance is very, very small compared to external resistance, current is maximum, right? So in case of, right, domestic AC, the voltage is 220 volt. If it is short circuited, right, the resistance is 0. 240 divided by 0, almost infinity. A very high value of current flows in the circuit and that produces a large heating effect and that circuit catches fire, right? And in this case, what is terminal potential difference? Terminal potential difference V is equal to IR is equal to I into 0 is equal to 0, right? In short circuit, the terminal potential difference across a cell, right, is equal to 0. Right. Now, we'll take comparison of EMF E and terminal potential difference V of cell. Now this is EMF E, terminal potential difference V. Now the same terminal potential difference is simply called as potential difference. So number one, so EMF of cell is maximum potential difference across terminals of cell in open circuit. Number two, right, potential difference is the difference in potential between, right, two points in a closed circuit. So potential difference is measured using a device called as voltmeter, and EMF is measured using a device called as potentiometer that we will discuss in the next classes. Now the second one, right, now this EMF provides, right, or EMF maintains a constant potential difference in a closed circuit. EMF maintains a constant potential difference in a circuit. Now, potential difference maintains a steady current in a closed circuit. So, the function of EMF is to provide potential difference to a closed circuit, and the function of potential difference is to maintain, right, a steady current in the circuit. Is it clear? So, though EMF and potential difference are measured in terms of volt, they are not same, they are different, right? Right, EMF is different from potential difference. Now the third one, so EMF, right, of cell is independent of circuit resistance. It is independent of circuit resistance, right? That is external resistance R, and depends on nature of electrodes and nature of electrolyte. Nature of electrode and nature of electrolyte. Here, right, this potential difference depends on circuit resistance and current in the closed circuit. It depends upon circuit resistance and circuit EMF. So generally the term EMF is used for a source of voltage like a cell, a battery or an AC generator. The term potential difference is used, right, used where there is a voltage or between 2 points, or there is a difference in potential between 2 points. Now we will take note this circuit analysis. Circuit analysis means, right, in any circuit, calculate the value of currents and potential differences in terms of EMF, internal resistance and external resistance, right? Now it is circuit analysis means calculation of currents and potential differences, right, in a circuit in terms of EMF, internal resistance of cell and external resistance. This is called circuit analysis. We can have various numerical problems, right, to analyze the circuit. Suppose we take example 1. Now we have a circuit. So R1, R2 connected to a cell of EMF E, internal resistance R. Right. When the circuit is closed, a current flows through the circuit. Now, from the knowledge of combination of resistors, we know that R1 and R2 are in series, therefore the same current flows through R1 and R2. Now potential difference across each resistance is different. Now let V1 be potential difference across, right, R1, and V2 be potential difference across R2. Now the total potential difference V is equal to V1 plus V2. Here V is equal to V1 plus V2 is the terminal potential difference or potential difference provided by the cell across a series combination of resistors. Now, right, to calculate current we need to calculate, right, effective resistance Rs is equal to R1 plus R2. Now second one, current I is equal to EMF by, now what is external resistance? It is the effective resistance of the combination. So Rs plus R. So we can calculate the current. Third one, what is potential difference across R1? V1 is equal to I into R1, because here we have given 4 values: EMF of cell, internal resistance of cell and 2 external resistances. And what is V2? V2 is equal to I into R. V2 is equal to I into R. Now fourth one, what is potential difference? V is equal to V1 plus V2, that is equal to I1 R1 plus I2 R. I1 R1 plus I2 R2, right? Now this is called circuit analysis, that is calculation of currents and potential differences in terms of EMF, internal resistance and external resistance. We will take example 2. Example 2. Now we have two resistors R1 and R2. Connected in parallel. Now this combination is connected to a cell of EMF E and internal resistance R through a key. When key is closed, a potential difference appears across the combination. That is terminal potential difference provided by the cell V. Now a current is drawn from the cell called main current. It flows from positive terminal to negative terminal. When it comes to the combination, it divides into I1 and I2. Say branch currents here, right? Now the same current I flows to the negative terminal. Here it is an electrical circuit in which two resistors are in parallel. Circuit analysis means calculation of currents and potential difference, right? Now number 1, we have effective resistance Rp is equal to R1 R2 by R1 plus R2. Number 2, main current in the circuit I is equal to E by Rp plus R. Now third one, potential difference V is equal to I into Rp. Potential difference V is equal to I into Rp, the product of current and resistance. Fourth one, we have I1 is equal to V by R1 and I2 is equal to V by R2. So we can calculate the current. Or by using branch current formula, I1 plus I2 is equal to I1 is equal to IR1 by R1 plus R2 and I2 is equal to IR2 IR1 by R1 plus R2, or even directly I2 is equal to I minus I1, but this branch current formula can be used only if two resistances are in parallel, right? Otherwise we cannot use this branch current formula. Then we can use V is equal to I into Rp. Suppose three resistors are there, then I1 is equal to V by R1, I2 is equal to V by R2, I3 is equal to V by R3, etc. Right? The same thing can be applied if resistors are in series and parallel. You find the effective resistance and then find current in the circuit and then mark various currents flowing through various resistors and potential difference across them. This is Ohm's law applied to a circuit, and this is from Ohm's law.